Today's speaker earned his PhD at the University of Oklahoma with excellent work developing microwave sensing with Rydberg atoms. Between earning his PhD and arriving at ColdQuanta, Dr. Fan worked as a postdoctoral associate on quantum memory with rare earth ion-doped crystals at the US Army Research Laboratory and the University of Maryland. Dr. Fan's efforts at ColdQuanta focus on developing quantum-enhanced microwave sensing technology. His activities range from fundamental research through product development. Esteemed quantum enthusiasts, Dr. Haoquan Fan will now educate us on microwave sensing with Rydberg atoms.
Thank you very much. So before my talk, please be aware that ColdQuanta staff are excited to describe our quantum control abilities in a lot of topics. Welcome to join us in this webinar in the future. If you search the word microwave on the internet, you probably will get a lot of pictures like this. Microwave is a form of energy. There is a microwave source in the oven. They can be used to heat food, water, although microwave is not direct heat. Microwaves can be described as sine wave function. There are certain specifics to describe it. The time to do one cycle is period of t. The inverse of t is frequency, means how many times the field oscillates in 1 second. And then the amplitude. It measures the value from the top of the oscillation to the bottom. In this picture, the three waves have the same frequency and amplitude, but at a certain place of the coordinate, the values are different. We say they have different phases, and also polarization. It describes the geometrical orientation of oscillations. For microwave, it could be linear, circular, elliptical, etc. A typical way to detect microwave is to use a dipole antenna like this. A dipole antenna will take a part of the energy of microwave and convert it into electric signal that can be readable. To improve the performance, people develop a lot of different geometrical antennas like this. These antennas have certain way to enhance the intensity of the target microwave. For example, for this dish microwave antenna, the microwave will be focused onto this point so that the field will be enhanced. This method can be traced back to 1880s. Hertz first proved the existence of microwaves in 1880s. The unit of frequency was named as Hertz in his honor. A dipole antenna similar to this was used to detect microwave, and the dipole antenna was later developed into standard antenna, which is to calibrate the intensity of the microwave and the other microwave devices. This antenna is also called traceable microwave antennas or standard antennas. This is the primary method to establish traceable microwave field measurement, and the method is still in use today. The importance of calibration means that standard antenna must be accurate, repeatable, convenient, and traceable. Since the standard antenna was first developed in 1960s, the minimum detectable field, sensitivity, and accuracy are greatly improved because of the development in technology in electrical engineering. However, this method has its limitations. Standard antenna will focus on geometry in which the variation in construction can happen. In addition, people need to focus on developing theory to these antennas. Since all these antennas are made of metal, they can disturb the field, especially in near field region. The reproducibility is limited, and the standard antenna will change because of aging. The size of the antenna is dependent on the wavelength of the microwave, typically half of its wavelength. So it is hard to build antennas in far infrared region or terahertz region, because the antenna will be too small to produce in this region. Because of these limitations, standard antenna usually exist in large laboratories like NIST in the United States. Atoms have many critical features in sensing area. People are thinking if atoms could be used as microwave detectors. Atoms have accurate properties. The measurements using atoms link to fundamental constants of atoms of physics, which can lead to self-calibrated devices or features. And these atoms are in dilute atomic gas, which is free of metal, so they will not disturb the field. Atomic systems are stable quantum objects. It means the properties are stable, while standard antenna using dipole antenna will change because of aging. For microwave measurement, the atomic system will not be size dependent, so it can cover larger frequency range without any size change. The experimental setup was simple because of development in AMO community for a lot of years, and can be scaled to portable microwave devices without too much effort. In fact, atoms are promising for many applications, such as atomic clock, sensors, or quantum information process. For atomic clock, it has been developed from 1950s to now. The best atomic clock can be stable to 10 to the negative 18, which is much more stable and precise than any other clocks. The atoms can also be used as sensors, for example, to measure magnetic field or electric field. The measurements are so precise that the fundamental constants of physics can be deduced or measured directly through sensing process. The basic element of quantum information process, qubit, can be encoded in atomic systems. Some atomic systems have been proved with non-coherence time so that a quantum operation can be carried out. For atoms, there are energy levels outside the atomic core, and these energy levels are discrete according to quantum mechanics. Taking rubidium, for example. From the ground state to the intermediate state, the energy difference is about that of 780 nanometer laser photons. When the levels are far away from atomic core, the levels are closer to each other. People use n to describe it, which is principal quantum number. We can see the energy at this regime. They seem almost continuous, but if we zoom it in, we can see that they are still discrete. The energy difference between the n is about a gigahertz to terahertz, which could be coupled to microwave field for sensing. Rydberg atoms are atoms with one electron excited to Rydberg states. In experiment, we use alkali atoms with principal quantum number from 20 to 100. These hydrogen-like atoms have exaggerated properties like size, lifetime, and dipole moments. And these exaggerated properties will have n-scaling laws like this. Especially, Rydberg atoms are quite sensitive to external perturbations. The external perturbations could be applied to external fields or fields created by other particles. This leads to a vast majority of research using Rydberg atoms. The motivation of our work is to build electrometry with Rydberg atoms, considering Rydberg atoms are sensitive to microwave electric field and have narrow bandwidths. The basic idea of the method is to detect a microwave E field through a coherent 3-photon process, using each atom as interferometer. Rydberg atoms can be microwave to optical transducers. The measurements can be calibrated by the properties of Rydberg atoms. So the method can lead to self-calibrated devices which could overcome the limitations of dipole antennas. Interesting physical phenomena like 4-level system with Rydberg states or Rydberg interaction could be studied using this setup, which could in turn be used to improve the measurements. We use alkali atoms to perform the microwave electric field measurement, like rubidium or cesium in this column. In this quantum, there's only one electron in the outer shell. The electron is called a valence electron. This feature will make the experiment easier than atoms in other quantums. The atomic spectrum is available because the spectrum of rubidium or cesium has been investigated for tens of years in AMO community. The atoms are stable atomic gas at room temperature, which is convenient for many applications. And the colors of lasers are also available. How to use Rydberg atoms to transform microwave intensity to optical readout? We are going to use a spectral technique called electromagnetically induced transparency for EIT. EIT is a quantum interference effect that permits the light going through an otherwise opaque atomic media by definition. It's basically like this. Suppose there's a light going through atomic media. If the color is unresonant of these two levels, the light will be absorbed, giving a spectrum like this. If there's a light going through atomic media at the same time, and unresonant between these two states, the absorbed light will go through atomic media, giving a peak in the transmitted spectrum. This is EIT, and this peak is called EIT window. In our experiment, we use a 4-level system like this. A probe laser will give a spectrum like this. With the coupling laser, the EIT window appears like this. When the microwave is coupled between two Rydberg states, the EIT window will split it. The frequency distance of the splitting is proportional to the Rabi frequency of the microwave, therefore proportional to the electric field amplitude here. The sensitivity here is very large is because the transition dipole moment mu here is very large. So how large is the transition dipole moment? We calculated the transition dipole moment for different transitions between Rydberg states. The dashed line here is a D29 transition of alkaline atoms. We can see that the transition dipole moments between Rydberg states could be thousands times larger than the D29 transition here. This is the calculated sensitivity and the short noise limit. We can see the sensitivity could be 8 to 10 orders better than the dipole antenna. Of course, in experiment, there are technical noises. But our experimental data will show with the multi-state setup, the sensitivity will be already several orders better than the current standard antennas. This is the calculated frequencies between Rydberg states versus the principal quantum number. We can see just by changing the principal quantum number here, the method can cover a larger frequency range from gigahertz to terahertz. You probably will ask, how about the microwave is below 1 gigahertz? As we could see from the calculation, and the principal quantum number is around 100 or even larger when the microwave is below gigahertz. In this regime, the Rydberg atoms are close to ionization point, and the experiment is hard to perform. Because in this region, it needs a stronger coupling light, while the signal to noise ratio of EIT window is getting worse. It turns out there's an alternative way to detect microwave here. Instead of coupling microwave between two Rydberg states, people find microwave can generate fluctuating states around the Rydberg level like this. And the states are separated by integer times of the frequency of microwave. In experiment, we will observe EIT with sidebands. This method can cover from 20 megahertz to 500 megahertz. But in this way, the sensitivity will be limited because one needs to a strong microwave field to generate sidebands. In this talk, we're going to still focus on the idea of coupling microwave between two Rydberg states. This is the experimental setup. The probe light and the coupling light are in counterpropagating scheme interacting with the alkyl atoms in a vapor cell here. The microwave is generated by a Hall antenna and resonant in between two adjacent Rydberg states. The probe light is a diode laser, and the coupling light is a frequency double laser. The signal is captured by a photodiode. The setup is free of vacuum system and independent of wavelength of the microwave. So it can be miniaturized and developed into portable standard apparatus in the future. How to determine the microwave E field? The frequency distance of the splitting is proportional to the Rabi frequency like this. This is called out-of-the-tongue splitting. We can derive the microwave electric field versus the splitting of the EIT signal like this. This is just the plot of the electric field amplitude versus the peak splitting. We can see it's basically linear as expected. The splitting uncertainty here is less than 0.5%, and the dipole moment uncertainty is roughly 1%. These numbers are pretty conservative, which means they could be larger than they really are. For the microwave field is low, the splitting cannot be resolved directly by out-of-the-tongue splitting. The RF field can be detected by observing the transmission change of the spectrum. Here's the raw data of the transmission and the different electric field amplitude of the microwave. Here is just the plot unresonant. We can see just by doing this, the lowest detectable field sensitivity is almost 2 orders better than the traditional standard antennas. Later, I will talk, the sensitivity has a long way to go. But first, let's go to the limitation here first. The modest setup of microwave sensing have limitations because the atoms at the room temperature are always moving. This feature will strongly limit sensitivity to further extent. Cold atomic system is a nice option given the atoms are cold and almost stay still for a certain time. The environment is clean. Of course, there are overhead here. People need to construct a cooling system, and the cooling system will bring metal and stray fields around the atomic system, which could interfere with the microwave measurements. For hot atoms, the atoms could be contained in a very simple glass cell like this. Hot atoms will save a lot of overhead, but there are fundamental limitations in terms of sensing. One of the main limitations is the EIT is broadened by residual Doppler effect. The EIT method using counterpropagating scheme, which is supposed to cancel the Doppler effect. When the colors of the two lights are the same, Doppler effect can be nicely canceled. But in the Rydberg EIT scheme, the colors of two laser beams are quite different. In this case, there are residual Doppler effect. This will broaden the width of EIT to megahertz region. So the sensitivity of the microwave sensing is limited. One could use 3-photon process to cancel the residual Doppler effect. The excitation level is like this. The wavelength of the 3-photon basically will have this relation. The basically mean the wave vector of the 3 photons will be 0. This will make the EIT width determined by the lifetime of Rydberg states, which could be in kilohertz regime. The time for atom interacting with the light is another important factor in the measurement. The atoms will see the lasers as a pulse of light whose width is determined by the time for them to travel through. This will need to broaden the signal known as transit time broadening. It is proportional to the velocity of atoms and the inverse beam size. We change the beam size to observe the microwave measurement and find as the transit time rate decreases, the transmission will increase. It means the sensitivity will be higher if the atoms stay longer in the interaction area. In some sensor experiment, such as atomic magnetometer or clock, people fill buffer gas inside the vapor cell so that atoms will stay in the interaction region longer. This technique is good for clocks or magnetometers because the measurement is dependent on the ground states, which is insensitive to collisions. For Rydberg atoms, they are quite sensitive to external perturbations. The collision between Rydberg atoms and the buffer gas will destroy the Rydberg states. So the buffer gas method does not work for Rydberg atoms, making transit time broadening a fundamental limitation for microwave sensing. The collision is an important factor contributing to dephasing effect. It is proportional to the cross-section, density of atoms, and the velocity of the atoms. It can be observed by measuring the EIT width at different temperatures. At this temperature range, the main change is the density change, while the velocity of atoms does not change much. For microwave measurement, the higher the collision rate will lower the absorption, thus will decrease the sensitivity of the measurement. In a lot of applications, people like to measure the field distribution to subwavelength scale. But using a dipole antenna, it is hard. It's like you want to surf on a wave, but the dipole antenna will severely disturb the wave. For a microwave electric field, if a dipole antenna is inside, it is made of metal, and the size is large, comparable to the wavelength of the microwave. So the field is more or less disturbed because of metal, while the atomic gas barely disturbs the target field. This advantage could need direct subwavelength measurement, near field measurement, etc. The experimental setup for subwavelength measurement is like this. A vapor cell is placed in between a horn antenna and an aluminum plate, while the standing wave of microwave pattern is formed. The image is formed by a lens and taken by a CCD camera like this. The wavelength of microwave is choosing larger than the size of a vapor cell to minimize the scatter effect. This is the simulated results. Here's the horn antenna. This is the aluminum plate. In between is the standing wave pattern. This is our vapor cell here. We just image the region which is relatively uniform in the beam propagation direction like this. So this is the imaging. If we just extract the center line here and plot like this, we can see the experimental data is quite matched with the simulation results. It gives the spatial resolution of 66 microns, which is lambda over 650, with very high field resolution. These numbers are limited by our imaging system and CCD camera, which could be improved a lot with more engineering work. To show that in near field region, subwavelength imaging can also be carried out, we investigate the microwave electric field above a coplanar waveguide, short for CPW. The setup is almost the same as a horn antenna experiment, just changing the horn antenna to waveguide. This is the profile of the experiment, and this is what it really looks like in experiment. Still, this is the simulated results, and this is the measurement results. We still exaggerate the set line here and plot them together. They match with each other very well. And we also fit our experimental data with the near field pattern of microwave. It fits quite well. Still, this experiment gives very high spatial resolution. The near field measurement is promising for many applications, for example, high frequency circuit design. For example, one could measure the near field pattern of high frequency circuit to see if there's any defect in the design or manufacturing process. Another example is atomic sensor could also be used to calibrate the microwave components. For example, a waveguide like this. One could put atoms or vapor cells inside the waveguide and directly measure the field pattern in the waveguide. to see if the waveguide meets the requirement of the design. The main application for microwave is to transfer information. Can atoms be information receivers? A lot of applications using FM, AM, or PM waves to transfer information. This is the AM feature, and this is the FM feature. The signal can be demodulated like this. It turns out that AM, FM, or this PM waves can be detected by atoms and read through atomic spectroscopy. Here is actually an example of audio signal read by atoms. The audio signal is encoded in gigahertz wave and AM modulated, and then sent through free space to atomic media. A real-time guitar recording is a good example for atomic receiver. Two different guitars are used to play music. The sound of music is programmed into two different microwave sources and radiated into free space. An atomic vapor cell containing two species of atoms, and then the two pieces of music are detected by atoms in vapor cells. The readout through two channels without disturbance. I got the recording by atoms through Dr. Chris Holloway. Here's what he hear like. Nice music, right? Oh. Oh. Yeah. It turns out that a digital signal can also be detected by atoms. Microwaves is unresonant between two Rydberg states. The digital signal changes the intensity of the transmitted probe light. The channel capacity is this amount. The system holds a significant promise to become one of the small numbers of useful technologies operating in quantum region, although the channel capacity is not quite impressive for the initial work. This approach also promising to operate at high frequency for 100 gigahertz, for example. This is the digital when probe. This is the digital look like when probed by atoms. These applications are designed from 1 gigahertz to 100 gigahertz. Can Rydberg atoms also be read out for terahertz or far infrared waves? The answer is yes. Here's an example. A terahertz beam goes through an object and hits the atoms here. An optical camera reads the fluorescence and emits the terahertz beam. In this experiment, the frequency is 0.55 terahertz, but the method can be applied to 0.1 to 10 terahertz if needed. The resolution is high, and also it has very high emission, fast emission rate. The sensitivity here is also very high. These features are promising for many applications using terahertz technologies. As our communications relies on microwave, more microwave sources are needed, and the frequencies of microwave go higher. For example, 5 gigahertz technology compared to the current ones. These microwave technologies will consume more and more energy and may be harmful to human health. Theory shows that Rydberg atoms can detect microwave with much higher sensitivity. This will lower the microwave intensity a lot for a lot of communication applications. Thus will save the environment and human lives. People are searching ways to improve the sensitivity of microwave sensing measurement. The main idea is to increase signal-to-noise ratio of the spectroscopy. We can use interferometers optical or atomic mixers. One idea is to use Mach-Zehnder interferometer with homodyne detection. The setup is shown in this figure. The probe beam is split by a 50-50 beam splitter. One arm goes to the vapor cell interacting with the atoms and the vapor cell and microwave. The other arm is local oscillator. We place a neutral density attenuator here to make sure the local oscillator is much stronger than the interacting beam. The two beams will interfere in another beam splitter and captured by a differential photodiode. This is a homodyne detection. For two channels, for the signal part, the signal will have inverse phase. So the subtraction will enhance the signal, while the noises will out of phase. So the subtraction will cancel the noise. Of course, the signal will be also enhanced by the strong local oscillator here. This is just the one single trace with and without the Mach-Zehnder interferometer. We can see the signal to noise ratio of the EIT is enhanced a lot, basically a factor of 20. By doing this, we improve the sensitivity is 1 order higher than the previous one. Another example is to use atoms as mixers. The experiment still use EIT as primary readout scheme. A strong microwave is unresonant between two Rydberg states, working as a local oscillator. A signal microwave is coupled with a little detuning here. In this way, they act as a mixer for the two microwaves. And we use optical readout here. Then the signal to noise ratio will be enhanced a lot. By doing this, we get the sensitivity, which is almost 2 orders better than the previous one. Here is the comparison of atom-based method to dipole antenna. The minimum detectable field and the sensitivity is almost 5 orders better than the dipole antenna methods. The accuracy is also greatly improved. Especially, we achieve a very high spatial resolution, which is hard to do using dipole antenna method. And our measurement is absolute measurements, which is calibrated by the Rydberg Atoms itself, which needs to self-calibrate the features. While the calibration of standard antenna method will change because of aging. And our experimental setup is simple and independent of a wavelength of microwave. So it can be developed into portable standard antenna and microwave devices without much effort. So here's the conclusion. So I talked about Rydberg atoms can be used as microwave detectors and promising for next generation of standard antennas. This method of detection have a lot of applications. For example, both analog and digital microwave signal can be read out with Rydberg atoms. And I also mentioned cold atoms and hard atoms both have their advantages in microwave sensing. Thank you very much. If you have questions, please.
Right, thank you very much, Haoquan, for an excellent talk. We have a few questions here and more coming in. And Nathan has the first one, and he asked, how much does the phase noise of the microwave source influence the accuracy of the measurement?
This is a very good question. Actually, in our experiment, we have very narrow bandwidth. It means just several gigahertz or several megahertz. So the bandwidth is quite narrow. It will have noise rejection with this nature. And for phase noise, we could use other method to actually cancel it. For example, using this Mach-Zehnder interferometer, or use this atomic mixer to cancel the noise. Or this noise could also be monitored with this method. Actually, with the atomic mixer, we can measure the phase between these two microwaves. So yeah, this will be quite a noise rejected method.
All right, excellent. So we have a number of questions on the lasers. So the stability required of the coupling lasers to require the selection of N. Does it need to be stabilized to a megahertz level like the probe beam? And also, what are the line widths requirement for the probe and coupling laser?
Yeah, this is a very nice question. Actually, in our experimental setup, we require very narrow and stable lasers. For example, for both the coupling laser and the probe laser, in a lot of the sensing scheme, we require laser less than 100 kilohertz in instantaneous line widths. We usually have a number of ways to lock it. For example, you can use very high finance cavity to really lock it. Yeah, or you can lock it to some atomic reference. So, but yeah, the line width is roughly less than 100 kilohertz. If one wants to higher sensitivity, probably we need a even narrower line width of lasers.
And sticking with lasers, how about the tuning range that you need to span a wide range of incoming waves?
Oh, yeah, this is a good question. It depends on what you want to do. If you want to scan the whole feature of the EIT or all the tongue splitting, you probably will have at least have a tunable range of several tens of megahertz to see the whole features. Of course, you can also just make the laser stay at one point on resonant to monitor the intensity change. And to cover the larger frequency range, for example, gigahertz to terahertz, you need your laser, especially your coupling laser, to be tunable for the different Rydberg states. And this to do this, you will at least have the feature to tune the laser to maybe, of course, several nanometers in range to cover the whole frequency range. But for the single measurement of the microwave, you just need tens of megahertz.
All right, excellent, excellent. Hey, can you use DC dark shift to shift the Rydberg levels and tune the microwave frequency to which the atoms are sensitive?
Nice question. Yeah, that's why we can see that this method can cover from larger frequency range from gigahertz to terahertz. But if you just notice when we do the calculation, our transition are discrete. They are kind of certain points in the whole frequency range. In this case, you can just use some DC electric field to move the Rydberg levels so that it can cover the whole frequency range continuously. Yeah, this is a very good method, and people are using right now. Thank you.
So one of our listeners, he is wondering about the technical and/or measurement difference between minimum resolvable field and the minimum sensitivity. What's the difference between those two?
It's a nice question. For the sensitivity, actually, it's just well, you integrate the measurement of time to 1 second and get the signals to noise ratio to be 1. And then if you do that, the minimum field you can measure would reflect the sensitivity you are going to have. But if you increase the integration time, for example, to thousands of seconds, and then to see what's the minimum field you can detect, then that's the minimum field you can detect. So basically, the sensitivity just means you integrated the measurement time to 1 second, while the minimum detectable field means you integrate the measurement time to a very long time to see what's the minimum field you can detect. That's the difference.
Okay. How about polarization? Can you distinguish microwaves coming in with different polarization?
This is not a, this is the analyzed question. I did not include into this talk because time limitation here. Actually, you can, let's see if I can see any spectrum of here. Let's see. Yeah, okay. So basically, with microwave coupling between two Rydberg states, you will see the out-of-town splitting. Basically, you will have two peaks here. But if you rotate the polarization of your microwave, the center line will appear at a different polarization angle. So by measuring the height change of the center line here, you will know the polarization angle of your microwave. In this way, you can get the very accurate measurement of the polarization of the microwave. It now can be as precise as 1 degree, maybe 0.5 degree. Yeah. Thank you very much for this question. Yeah.
All right, that's exciting. But then we get to practical devices. What are the what size devices are the smallest Rydberg detectors out there for microwaves, and how small do you think they'll get in the near future?
That's a nice question. Yeah, I think it can be as small as needed, because the measurements will really independent of the wavelength of the microwave. So so the wave cell can be really small. But we also need to be aware that the signal to noise ratio of our measurement will be dependent on the how many atoms will be participating in the interaction. So the smaller of the wave cell will lower the number of atoms in the interaction. So basically the size of the wave cell is kind of limited by your signal to noise ratio of your detection scheme. Yeah. As long as you have acceptable signal to noise ratio, it can be as small as needed. Thank you.
When comparing the advantages of Rydberg sensors to antennas, you noted that the metal antenna can disturb the field you're trying to detect. But then when you're building your Rydberg sensor, you also have it surrounded by optics and lasers and such. And do those not interfere with the signal that you're trying to measure, or how do you get around that?
Yeah, that's a nice question. It basically the metal will disturb the field is basically means that to accurately measure the electric field amplitude of field distribution, you need the dipole antenna. The size is comparable to the wavelength of the microwave. In this way, it can very severely disturb the targeted field. But for our wave cell, as long as you keep this two lenses far away to the wave cell, and the distance is larger than the wavelength of the microwave, it will barely have disturbance. Actually, in our case, the microwave is basically just a millimeter region, right, or centimeters. The length of here could be roughly. So this could be very, very far away, and the disturbance would be minimized, given this this feature. So the disturbance of this can be negligible compared to the dipole antenna cases. Thank you.
And are there any fundamental limits on channels, on the number of channels that you can receive with a single cloud of atoms, or is there a technical limit? What really sets the limit on how many channels you can pull out?
You mean the analog detection scheme or the digital detector scheme? if you mean the analog detector scheme, I used just the example, like two channels of microwave can be detected simultaneously with Rydberg atoms. They basically have two species here. I guess there's no limitation here as long as you choose. This detection can be separated by the channel of detection. Basically, in this case, we have just one photodiode here to receive each channel. But if you have multi beams here, and each beam will detect a different channel, I cannot see there's a limitation of the channel limitation here. So I will say this is just the experimental scheme, but the channels can be expanded a lot. Thank you.
So you could, for example, use a grating and a CCD instead of a photodiode to get a higher channel density.
That's correct.
Okay. So let's see. How about antenna gain? How are the absorption cross sections of a vapor cell and a metal antenna compared?
Well, that's a good question. In most of the experiments, we can see our vapor cell size is quite small compared to the wavelength of microwave. Some people said the cross section of receiving the microwave is quite small. Although the cross section is small, we still can get a very high sensitive measurement here, which means our method is actually more sensitive than we think. But our advantage here is that we can get a very small cross section of the microwave while still get a high sensitivity and high spatial resolution using the Rydberg atom detections. While for dipole antenna, of course, it have higher cross section and the field gain, but basically the standard antenna it will still disturb the field, and you need a fair amount of the microwave intensity to get a good signal to noise ratio of your electric readout. So I'll take a small cross section of microwave as an advantage of our sensing instead of disadvantage here. So, but it's an open question to discuss. Thank you.
There's a question about jamming. Does the quantized nature of sensors make resistant to jammers?
For this question, I'm not quite sure. I guess the resistance, our method barely disturb the target field, which is a nice feature, which means if you read this in terms of jamming or resistance, I would say the resistance probably is very high, basically infinity, compared when you do measurement on using dipole antenna, you probably will choose 50 ohm or 75 ohm, while in free space it's roughly equal to 377 ohm, right? So I would say our resistance will be equally to infinity. I hope it's right. Thank you.
All right, great. Well, Haoquan, I think we've answered a good number of questions, and people are well educated. Really appreciate you taking the time to give this webinar here.
Very much. Last, I want to mention that we have a YouTube channel. Please subscribe for more updates in the future. We have exciting updates in the future. Thank you very much.
Thank you all for your attention. I hope you enjoy the rest of your day, evening, or night. Goodbye.